All right, fluid friction part 2. This time, we're going to look at a situation where the object is moving quickly, a stalled plane, in which case the friction force is not related to the velocity directly, but proportional to the velocity or speed squared. This is a turbulent situation. And it's also related to work, so some validation for this is work has the form of force times distance. The work done on the plane by the air then is delta K, and delta K is change in 1/2 mv squared. So we can solve for force out of this and recognize that force is this constant times v squared, which gives us the validation that the force is related to the velocity squared. So we're going to go with that. And when the plane is flying at some speed, the engine's going to stall. So the net force acting on the plane to slow it down is cv squared acting against the motion, so it's a minus. So here's a free body. Oh, the engine stalls. So we have mg, normal, they cancel out. We're not concerned about those. It's the fluid friction, the cv squared, acting in the opposite direction of the motion. Therefore, the acceleration is in that same direction. We have this initial speed v0. So that's the scenario drawn for you. So sum of fx is friction. What is it? Minus cv squared, which of course is ma. So, writing the differential equation, mdv dt is minus cv squared. And now, simply, let's solve it. So, let's separate the variables. mdv equals minus cv squared dt, and then bring the v's over to one side. 1 over v squared dv is minus c over m dt. Now we can integrate. Let's do so. The velocity goes from v0 to v, while the time goes from 0 to t. At time t is equal to 0, v is equal to the initial velocity, v0. So, 1 over v squared is v to the minus 2. Don't think that's natural log. The integral of 1 over v squared. And, there we go. So we have minus 1 over v from v0 to v, minus c over m, t from 0 to t. Minus 1 over v plus 1 over v0 is minus c over m t. So 1 over v, changing the sign here, is equal to 1 over v0 plus c over mt. And there's our velocity. Take the whole thing to the -1 power, and we got it. The acceleration will be easily forthcoming. dv dt, the derivative of 1 over v plus c over mt to the -1. So, let's use the chain rule, bring the -1 down, take this to the -2, times the derivative of what's inside with respect to time, which is c over m, and we get our coveted expression for the acceleration. Then position. Of course, it's the integral of velocity, so there is the integral of velocity. Note that this is to the -1 power. How do we do this? Well, I'm going to rewrite this in terms of two constants a and b, where a is 1 over v0, b is c over m. So that simplifies this a little bit. Now, something with the variable here of note, t, to the -1 power, so we're probably going to end up with natural log. Let's see how that works. So, solving for x, indeed, we have the natural log, and this is just making it simple for us to track it here. We have natural log of a plus bt. Of course, we bring the b, this constant, down underneath, so there we go. And b was c over m, so 1 over b. So we didn't get confused here. We put the actual values for b and a back in. And now let's carry it out. So we have x equals m over c. Putting in the t, we got t here. And then subtracting off, the same thing with 0 in for t. We end up with just the 1 over v0. So we have the difference between two natural logs, and you know that that is the natural log of the ratio. So there's the ratio. 1 over v0 divided by 1 over v0 is like multiplying by v0. And so finally we have now, how does the position depend on the velocity? So let's find x as a function of v. So here's our solution for x as a function of time. We also had that 1 over v minus 1 over v0 equals c over mt. Well, you might notice correlation here with this term and this term. Oh, they're very similar. C over mt, this just has v0. Let's multiply this through by v0 and see what that gives us. That's what it gives us. Notice now that this term and this term are the same. So let's sub in v0 over v minus 1 for this term here. And there it is. It all worked out for us. X is a function of v. M over c ln of 1 plus this whole thing is v0 over v minus 1. So the 1's go away, and we just have v0 over v left. And that's a wonderful expression for how the position is related to the velocity, or is dependent on the velocity. Let's check out one more way to get x as a function of v. So sum of F is minus CV squared, the fluid friction, the frictional resistance. And of course that's MA, which is M dV dt. Now we can use the chain rule idea, which is M dV dt is M dx dt dV dx. And there's dV dt, so there's MA, dx's go away. But we're interested more so in the dx dt here, which of course is V. mv dv dx. So minus cv squared is mv dv dx. Obviously, we have same velocity on both sides, so one of those v's goes away. We have bring the m to the other side. Minus c over m dx equals dv over v, or 1 over v dv. Now let's integrate. So I'll put the integral there. X goes from 0 to x, v goes from v0 to v. So we have minus c over mx equals natural log of v over v0. X is minus m over c natural log of v over v0. So we have discovered the relationship between x and v. And it's the same thing we had before.